planet Earth was created from interstellar stardust 4.55 billion years ago. To help understand the enormity of this timescale, imagine if our planet's eventful history was compressed into the 24 hours of a single day. At midnight, the infant Earth was born. At 8 minutes past, the entire globe melted. And its molten iron core generated a magnetic shield that protects us from harmful cosmic rays. At 16 minutes past midnight, a cataclysmic collision created our moon. After this turbulent and violent beginning, the surface cooled, a crust formed, and water settled on the surface. Then, just before 1 o'clock in the morning, the scene was set for the most important chapter in the history of our planet, the origin of life. In this remote corner of Western Australia lie clues to the origin of life on Earth. These unique dome structures were built by countless tiny microbes. They're living remnants of organisms that dominated life on our planet for billions of years.
Coming to this place where the stromatolites grow in their solitude on this very quiet shoreline, it really feels like stepping back through time 3.5 billion years ago to the very early Earth.
One of the greatest geological finds of our time are fossil stromatolites that were alive billions of years ago.
And that's really fascinating because it means that life evolved on this planet very early and very fast.
Tiny organisms had brought about a complete transformation of our planet and created a world where life could survive and flourish. Early Earth was hostile, an extreme place for life to emerge. It was smothered in a thick, turbulent atmosphere. There was no oxygen, and the ultraviolet radiation was lethal.
When we think of early Earth, we must recognize it was not a Garden of Eden. There were no clear blue oceans. There was no clear water. There were no plants. There was no life at all.
The young sun was weaker than it is today. Its feeble light would have barely penetrated the noxious atmosphere. Carbon dioxide would have mixed with the pungent smell of hydrogen sulfide.
Since the atmosphere was thicker and dominated by CO2, the Earth had a reddish tinge to it. It didn't have the familiar blue sky. The oceans would have had an olive green color rather than our familiar blue color.
For the first 600 million years of its life, our planet was constantly battered by comets and asteroids. This is known as the Great Bombardment. missiles could measure 300 miles across. Their cataclysmic impacts melted the Earth's crust and vaporized the oceans. With extreme temperatures and acid rain, it would have been impossible for a human to survive here. But amazingly, in the midst of all this violence, the first spark of life took hold. Billions of years later, Earth is teeming with life. Covered with an incredible variety of plants and animals. But even now, hidden away in remote corners of our planet, simple life forms can be found in conditions as extreme as primitive Earth. Microbiologist Penny Boston and her colleague Diana Northup are on an expedition to southern Mexico to find out how life could have survived on early Earth. Hidden in the depths of this tropical rainforest is a cave, Cueva de Villaluz. This modern hell on Earth is filled with hydrogen sulfide, a gas that was abundant on our early planet.
These relic or antique environments like Cueva de Villaluz offer the same kinds of environments that we would have found on early Earth, and we're hoping to get clues to work backwards from those. As you approach the cave, you begin to get these faint whiffs of the rotten egg smell. And as you get closer to the cave, this becomes more intense.
To survive inside the cave, Penny and Diana have to wear gas masks. Hydrogen sulfide is extremely poisonous.
No leak.
Have you got everything in there?
I think I got everything.
At the levels at which humans can't live very long in hydrogen sulfide, you don't smell it at all. And it will just simply cause you to go unconscious and die very quickly.
The two biologists have come here to investigate what kind of life forms can survive inside the cave. This is a dangerous place to explore. Hydrogen sulfide gas escapes from deep volcanic fissures, reacts with the water, and coats the cave walls with concentrated sulfuric acid.
The longer it sits there on the walls, the more acid it becomes. And so eventually, by the time the drop is falling on you, it's a very, very acid environment.
The slime layer feels pretty thick today.
It's very fatiguing, and even with the protective masks that we have, we pick up loads of toxic gas through our skins and perhaps through tiny leaks.
Oh, get out of those sweat tights to your left.
Despite the extreme conditions, Penny has discovered that primitive life is thriving inside the cave. Cueva de Villaluz has been nicknamed Snot Cave, after its colonies of slimy, single-celled bacteria the scientists call snotites.
The snotites are drippy, gooey, mucousy formations that look like stalactites, and that's why they were called snotites, but because they resemble strings of snot. We believe that the snotty, gooey stuff is to protect them against the extreme acidity, because when we measure the drips on the snotites, they are as extreme as battery acid. And so while we find that daunting, this is where they thrive.
Bacteria are the most primitive and most common organisms on Earth. They share the same definition of life as all plants and animals. They grow, adapt to their environment, and reproduce. Bacteria cells never have a nucleus, but they do contain DNA, the code of life, and reproduce by simple division, each one splitting into 2 identical cells. There are hundreds of thousands of bacteria in each snotite. Down in the underground streams, Penny has also found globby mats of bacteria which she has called phlegm balls. In fact, the cave is home to many different kinds of bacterial colonies. These primitive life forms are thriving in the noxious gases. The scientists have discovered that these bacteria derive their energy by converting hydrogen sulfide into sulfuric acid.
They take the hydrogen sulfide and they get chemical energy out of it. It doesn't poison them. It's home sweet home for them. And this is a pretty new finding for these organisms.
These bacteria are living in an environment similar to early Earth, and they could be the descendants of the very first life on Earth. But where did the very first bacteria come from? Like all life forms, bacteria are based on complex carbon molecules. Somehow, in the conditions of early Earth, lifeless carbon molecules miraculously started to make exact copies of themselves. But how these molecules began to self-replicate and then evolve into the first living cells remains perhaps the biggest mystery in all science. What scientists have discovered is that life began much sooner after the birth of the Earth than they had ever thought possible. For they have discovered that life was already thriving on the planet as early as 3 minutes to 4. The evidence for this early emergence of life has come from a team of geologists studying some of the oldest rocks on the planet in the remote regions of northwest Greenland. Geologist Stephen Morgeses has been searching for telltale traces of the most ancient life on Earth.
The geology of Greenland is unique. It contains a record of some of the earliest geological processes that we know of on the Earth. The rocks themselves are thought to be between 3.7 and 3.9 billion years in age.
These rocks would have experienced tremendous upheaval, and any fossils would have been destroyed. So Stephen had to look for evidence of life that was far more elusive.
There may have at one time been small fossils, microfossils, but under the conditions of heat and pressure that these rocks experienced, such fossils would have been disaggregated and destroyed. So what we have left behind then are chemical fingerprints of ancient bacteria or microbes.
All living things have a preference for carbon-12 when they absorb carbon from their surroundings. Stephen realized that he could use this vital clue to search for ancient life. Using a high-powered ion microprobe, Stephen found that the Greenland rocks contained a much higher amount of carbon-12 than expected. A sure indicator that life was present when these rocks were first deposited over 3.8 billion years ago. Here was the oldest evidence of life ever found.
It was a surprise for us to find evidence of ancient life in these rocks. We didn't know if it would be there. You know, just because the stage is set doesn't mean that the actors are present. But these samples here represent the first evidence we have, direct evidence of a biosphere on our planet.
But if life did start so early in Earth's history, where had the building blocks of life come from? Soon after its birth, a giant body collided with our planet. The outer layers were completely vaporized, creating our moon. Any complex carbon molecules that existed on Earth would have been entirely destroyed by the massive impact. So one theory for where they first came from, that's rapidly gaining support, suggests the molecules were delivered as ready-made packages from outer space.
Space is not very far away. Space is only about 20 kilometers that way. Now that's very close, and space is vast.
Astronomers used to think space was an empty vacuum, but astrobiologist Don Brownlee has been able to prove that the building blocks of life are common in space and regularly fall to Earth.
There are 40,000 tons of bits of comets and asteroids that impact the Earth every year. This is mostly in form of particles that are less than a millimeter in size. We breathe them, they're in the food that we eat, but they're very difficult to find. You can only find them in very special places.
To make sure Don has pristine samples, it's important the particles are caught before they fall through the Earth's atmosphere and become contaminated. To collect just a few milligrams from the thousands of tons of debris that fall each year, Don commissions a former ER-2 spy plane to fly at 65,000 feet, close to the edge of space. The space dust is collected on sticky pads attached to the upper surface of the wings. Back on Earth, Don Brownlee's colleagues have to slice the particles into tiny slithers before they can be chemically analyzed. Each particle is less than a tenth the thickness of a human hair. Don has discovered that the particles are rich in carbon molecules.
When you look at them in an electron microscope, you see this wonderful array of minerals and carbon and organic materials that are 4.55 billion years old, and we believe are the building blocks of life.
Huge amounts of debris left over from the creation of the solar system are still floating in space. But most of it is in the form of lumps of rock orbiting in the asteroid belt. One vital piece of evidence that supports the theory that the ingredients of life came from space is a very special meteorite picked up in Murchison, Australia in 1969.
It's a gold mine, this little chunk of meteorite which fell on Australia last year. For the past 6 months, they've been taking it apart and have discovered it contains amino acids, the building blocks of life.
This was the first time that amino acids had ever been detected in any material from space. Amino acids are carbon molecules that combine to form the proteins that are vital to all living organisms. NASA's Michael Zelensky has been researching the Murchison meteorite for 20 years. He believes that meteorites like Murchison would have been so commonplace in the early history of the Earth that they could have delivered vast quantities of amino acids from space.
Enough organics are present here that we think that meteorites like this provide to the early Earth its entire budget of organics. So all the organics in your body, all the carbon in your body, and in your lunch you had today, arrived on the Earth in carbonaceous chondrites like this.
More than 70 varieties of amino acids have been found inside meteorites, and 8 of them are the fundamental constituents of proteins found in living cells. During the Great Bombardment, throughout the early hours of the morning, billions of asteroids and comets may have seeded the Earth with the stuff of life. Compared to meteorites, comets may have delivered even greater quantities of amino acids. Some of these icy dust balls were the size of mountains, and up to a quarter of their mass could have been organic compounds. But when a giant comet struck the Earth, could these carbon compounds have withstood the immense impact?
That's good. Stop, stop.
Jennifer Blank, a geophysicist, has designed a unique experiment to see if the amino acids could survive the trauma of impact. Using a huge gas gun, she simulates the extreme pressures and temperatures that a comet experiences when it smashes into the Earth.
We set out to test whether or not materials would survive or whether they would break down. And we expected that, or we were hoping that some fraction would survive. And we figured the parts that didn't survive would break down into smaller components. But in fact, what we found was much more exciting.
In Jennifer's experiment, the gun fires a bullet at 10,000 miles an hour towards a target sample that represents the organic molecules inside a comet. The sample consists of a solution of 5 different amino acids, including glycine and proline, both present in every living cell. The mixture is then inserted into a hardened steel capsule. The impact from the gun will send a shockwave through the capsule, simulating the extremely high temperatures and pressures of a cometary impact.
I think it's very hard to just imagine what kinds of pressures were generating these experiments. If you think about going to the bottom of the ocean, the pressures you'll have there are only 100 times atmosphere. So these are hundreds of thousands of times atmospheric pressures.
Could Jennifer's experiment deliver the final proof that the building blocks of life did arrive from outer space?
Clear the room.
Using a large gas gun to simulate the colossal pressures of an impact, Jennifer Blank is about to find out whether comets could have delivered amino acids to Earth intact.
Okay, charging up. Okay, bringing up the X-rays. Okay, I'm going to external group. Ready to fire?
Go ahead.
Okay, then 3, 2, 1. 2, 1, fire.
The steel capsule was undamaged, but had its contents survived the impact. The once clear solution of amino acids had turned a tarry brown color. And when Jennifer analyzed its chemistry, she found that the material had not only withstood the colossal pressure, but it had transformed into a new compound. The energy of the impact had fused the amino acids into peptides, halfway towards building a protein.
We went from our initial small compounds, and here's an example of one of them, simple amino acid, and we used the energy associated with the impact to build larger molecules. Molecules like this. This is a peptide, and we showed that we could use the impact energy to grow larger molecules from the simplest building blocks of life.
Jennifer's experiment proves that not only can organic molecules survive an impact, but the immense pressures created can also produce complex molecules one stage closer to the origin of life. But the mystery of how and where these carbon molecules transformed into life still remains. Some scientists are now suggesting that these early carbon molecules trickle down into cracks in the Earth's crust, where the miracle of life began, protected from lethal radiation deep underground. Microbiologist James Hall has traveled from Princeton University in America to one of the deepest mines on Earth. With pioneering new research, he's discovered that microbial life can survive much deeper underground than ever thought possible. This mine in South Africa allows him to descend over 2 miles down through the Earth's crust.
The mining environment gives us this fantastic window into the deep subsurface. It's a unique scenario because there is nowhere else on planet Earth that allows you to have access to that sort of sample location at 3.5 kilometers deep.
It takes James 45 minutes to travel from the surface down to the deepest level of the mine. Conditions down here are extreme for any life forms. The temperature of the rock is 50 degrees Celsius, and the air pressure is twice as much as at the surface.
Morning.
Two miles down, James and his research colleagues are as deep as they can get. Microbial life existing down here survives without sunlight. And the only source of food is a diet of molecules from the surrounding rock.
Microorganisms have been shown potentially to be able to use these molecules to provide themselves with energy and support themselves completely independent of photosynthesis. And if we can prove that that is the case here, then that is very interesting because that adds credence to the idea that you could have life originating in the deep subsurface.
As the miners drill into the rock, they break through into ancient reservoirs of water, a haven for microorganisms.
So these organisms have just kind of been locked away in a small water pocket, and that may give us a lot of information about the ancestors to life and how life may have originated in one form or another.
Radioactive dating techniques have established that this water is 200 million years old, and it's teeming with microbes.
We're not sure how organisms can live in such extreme environments. The major thing is there's such low nutrient availability. There's nothing really for these guys to continually use and process to survive, and yet somehow they do. And the question is, how do they do it?
Right, 3, 2, 1. Go. And stop.
To find out how the microbes can survive so far from the Earth's surface, The team collects pristine samples of the ancient water. James will take these back to the lab where the microbes will be cultivated.
I get a very big sense of achievement if I can actually take something that's been isolated for 200 million years, put it in the laboratory and actually find out what it is this organism needs to survive.
In his makeshift lab near the mine, James is able to recreate the subterranean environment of the microbes. There is no oxygen in the rocks 2 miles down, so first he has to extract any oxygen from the test tubes. This experiment is designed to find out how the microbes derive their energy. After the test tubes are sterilized and protected in an oxygen-free tent, James mixes the microbes with different chemicals.
It turns out that in the deep subsurface there's an abundance of methane gas and ethane and propane. Now for you and I that's not a very exciting diet, but what we think is that these organisms may be taking that kind of gas and actually using that as a food to survive.
Their food supply is so limited, the bacteria derive only enough energy to divide and reproduce once every 1,000 years. The DNA inside these microbes will have hardly changed since the origin of life.
If we can isolate them, get them to grow and study their DNA, then this DNA may be like a snapshot back into the past of what microbes used to be like.
James's research is still in the early stages, but his unique experiment reveals that life could have started deep in the Earth's crust. During the Great Bombardment, the Earth's crust may not have been the only place where life could have survived. Another safe haven may have been the deep ocean. Volcanic activity was far more intense than it is today. Chemicals from deep inside the Earth would have spewed into the oceans. In the 1970s, marine biologists discovered volcanic vents deep on the ocean floor. They were amazed to find that primitive microbes thrive down here despite temperatures of over 100 degrees, acid eruptions, and a complete lack of sunlight. The microbial life appeared to derive its energy from the noxious hydrogen sulfide gas erupting from the vents. On early Earth, microbes may well have survived in very similar environments.
If all of the bombardment was occurring near the surface, survivors would be existing in just these kinds of hydrothermal vent communities, where there's abundant water and nutrients and heat and food in the form of chemical energy. It has been found that organisms collected there nowadays are genetically kin to some of the earliest organisms that we think existed on the Earth.
On our 24-hour clock, it was now 5 o'clock in the morning. The Great Bombardment was over. Most of the debris in the solar system had been swept up and there were far fewer violent impacts on Earth. Microbial life was able to emerge from its protective hiding places. It began to flourish close to the surface and take advantage of a new, powerful source of energy, the sun. These bacteria evolved a green pigment, chlorophyll, which enabled them to harness the sun's energy through photosynthesis and convert carbon dioxide into carbohydrates. As the Earth cooled, this new generation of cells began to spread across the oceans. immense colonies of green slime took over the world, and the greatest transformation in the history of our planet was set in motion. The best evidence of what primitive life looked like has been discovered in one of the remotest parts of our planet. These rocks have remained unchanged for 3.5 billion years. Here it's possible to walk on the ancient surface of early Earth. Martin van Kranendonk spends months at a time in this wilderness, studying the outcrops and producing maps for the Geological Survey of Western Australia. Hidden in a secret location amongst these rocks is one of the greatest geological discoveries of all time.
These are the oldest fossils in the world, at about 3.5 billion years old. And they're composed of stromatolites. And at this outcrop we can see two different types of structures that these creatures formed. First are these black mats that have wrinkly textures all through it. And the second are these larger domes that form these broad structures. The only way these could have formed is by the growth of microbes.
These fossilized stromatolites were built by ancient colonies of bacteria. Nearby are fossilized ripple marks, which suggest that these bacteria grew in shallow water.
And here you can see we've got a smaller structure that we call the Mickey Mouse ears, which is this beautiful doubly branching structure. And there's nothing else that we can think of which would make that except something that was growing on the bottom of the ocean.
Just 500 miles from their fossilized remains, the same organisms can be found alive today. These modern stromatolites are growing on the Western Australian coast in the shallow waters of Shark Bay. This is a safe haven for the stromatolites. The seawater is twice as salty as normal, which helps to discourage predators that feed on bacteria.
These big stromatolites are composed mostly of rock at the bottom, and the only living part of the stromatolite is a thin layer on top. And that thin layer on top is made up of microscopic blue-green bacteria called cyanobacteria.
These cyanobacteria, named after the color of their cells, use photosynthesis to collect energy from the sun. They secrete a sticky coating to shield them from ultraviolet radiation. As tiny pieces of dust and sediment settle on top of the sticky cells, the bacteria migrate closer to the surface to reach the light. The layers of sediment build up by about 0.5 millimeter a year, and over thousands of years create these dome-shaped structures. Many different shapes and sizes of stromatolites have been found fossilized in the rock. This suggests that by 3.46 billion years ago, stromatolites had lived on Earth long enough to evolve into a variety of different bacterial colonies.
We're looking at sort of a cross-section through the top of these cones and the layers that were laid down year after year. And the fact that they're all different sizes on this one surface shows that there was a colony of microorganisms growing on this one bedding plane. And that suggests to us that even in this very early time of Earth, there was a diverse community of microbes. And that's really fascinating because it means that life evolved on this planet very early and very fast.
It was still only 5:45 in the morning, and the most significant change in our planet was about to begin. Stromatolites had spread out across the entire planet. To derive their energy, they absorb sunlight and carbon dioxide from the atmosphere and produced a waste gas that would transform the entire planet: oxygen. At first, all the oxygen was absorbed into the oceans. Underwater volcanoes were spewing out iron from erupting lava. The iron dissolved in the seawater and chemically reacted with the oxygen. It fell as minute iron oxide particles to the ocean floor. Over the next 700 million years, the planet literally rusted. All the iron was turned into oxide, building up layer upon layer of what would become the most significant mineral deposits on Earth: iron ore.
Connect the stopper.
This is one of the largest mining operations in the world. The iron was originally deposited on the floor of an ancient ocean.
Control Blast 2, we're at the firing position. Stopper's connected. We'll fire in 10 seconds with a 5-second countdown.
Roger, Blast 2.
Here they excavate 500,000 tons of iron ore every week, worth $3 million Australian dollars.
4, 3, 2, 1, fire.
Thousands of these ancient layers of iron ore are exposed here in the Karijini Gorge, just 30 miles from the mine. As the water temperature changed with the seasons, the production of oxygen by the cyanobacteria varied. Different amounts of iron oxide were deposited at different times of the year, creating these distinct layers in the rock. This was a global phenomenon. Vast amounts of iron ore were laid down in similar deposits all over the world. On our day-long clock, it took more than 7 hours for all the iron to be removed from the oceans until 1 p.m. in the afternoon. When there was no iron left to react with, the excess oxygen from the stromatolites began to build up in the atmosphere. Slowly but surely the planet was transformed. Over the next 8 hours, the microbes raised the level of oxygen from less than 1% to the present level of 21%. The time was 9 p.m. Without the cyanobacteria, there would be no oxygen, and Earth would still be smothered in noxious gases. There would be no plants and animals, and humans would never have evolved.
Life has made this environment what we know. It's allowed us to live on the surface. It allows us to breathe. It allows large organisms like we are to function at very high rates of activity.
The oxygen also helped to protect life from the sun's lethal ultraviolet radiation. Molecules of oxygen began to break apart in the upper atmosphere and created a layer of ozone.
One of the fascinating properties of that is that it actually screens out, just sort of like a sunscreen does on your skin, screens out this harmful radiation.
With the protection of the ozone layer, life was finally able to evolve into much more complex organisms. It took only the last 3 hours of our 24-hour day for all the other life forms on our planet to evolve. The first multicellular life emerged at 6 minutes past 9 in the evening. The first fish at 22 minutes past 9. Insects at 20 to 10. Reptiles at 20 past 10. By 10 to 11 in the evening, dinosaurs roamed the Earth. The first primates appeared at 20 to midnight. And with just 30 seconds to go, the first humans made their appearance. Tiny microbes had ruled the planet for over 3 billion years, 2/3 of the history of the Earth.
It's only been the last 10% of the Earth's history where there was life on the surface of the Earth that you would see with your naked eye. So for most of Earth's history, life has basically been invisible on the Earth.
Over 1 billion or 2 billion years, the amount of oxygen that these little creatures produced was enough to actually change the entire atmosphere of the planet.
Multicellular life that we're most familiar with, animals, plants, their environment was made possible by the slow, toilsome task of bacteria to oxygenate the atmosphere.
These tiny organisms had transformed an entire planet. Without them, life as we know it would be impossible. Planet Earth was created from interstellar stardust 4.55 billion years ago. To help understand the enormity of this timescale, imagine if our planet's eventful history was compressed into the 24 hours of a single day. At midnight, the infant Earth was born. At 8 minutes past, the entire globe melted. And its molten iron core generated a magnetic shield that protects us from harmful cosmic rays. At 16 minutes past midnight, a cataclysmic collision created our moon. After this turbulent and violent beginning, the surface cooled, a crust formed, and water settled on the surface. Then, just before 1 o'clock in the morning, the scene was set for the most important chapter in the history of our planet, the origin of life. In this remote corner of Western Australia lie clues to the origin of life on Earth. These unique dome structures were built by countless tiny microbes. They're living remnants of organisms that dominated life on our planet for billions of years.
Coming to this place where the stromatolites